So welcome everyone to our STAMPS webinar series. It's a pleasure to introduce Dr. Ashley Villar. So anyone who's in astrostatistics would know how much of a driving force Ashley has been in getting the community together, especially for LSST science. So Ashley Villar is an assistant professor of astronomy at Harvard University, and she's also the co-chair of the LSST Informatics and Statistics Science Group. Ashley received her PhD in astronomy and astrophysics from Harvard. And after a PhD, she was a Simons Junior Fellow at Columbia University in the Flatiron Institute, and she then became a career development professor at Penn State. So Ashley's research focuses on data-driven analysis of optical transients, including core collapse, supernova, and kilonova. And she's particularly interested in representation learning for sparse multivariate light curves. And today she will talk about, I'll change your title.
Sorry.
Let's see here. Time domain astrophysics in the era of big data.
Yeah.
So Ashley, please take it from here.
No, thank you so much for having me. So I am really excited to discuss today some open statistical challenges in this field of time domain astrophysics, and I'll define what I mean by that. If it's allowed, I am very happy to take questions throughout. Is that not technologically not allowed?
Sure.
Okay, great.
That works.
Awesome. Yeah, so I can see you, and so if you raise your hand, I can call on it. And I can't emphasize enough, I love being interrupted and having interactive talks. So the talk really is the intersection of developing new data-driven methodologies, but for the explicit purpose of forwarding this field of time domain astrophysics. And I'm going to argue that we have to do this in unison because we really are reaching a point in time domain astrophysics where we have too much data to rely on our very traditional techniques of characterizing explosions we see in the sky. So let me take a small step back and define time domain astrophysics. To me, this is anything that's evolving on the night sky, on human timescales. So in cosmological and astrophysical context, something might be short-lived if it lasts for millions of years. But here I really mean like human timescales. The explosion of a star and its thermalized radioactive decay that we see as light really is only visible to us for maybe a month. And so as we see these bumps in the night, our job is to try to capture the photons of those events and use that in combination to high-energy astrophysical models to explain how massive stars live and die and create heavy elements that now populate our universe. Because it's a data talk, I want to be super clear about what type of data we think about. And my intro somewhat explains this, that I think a lot about multivariate but sparse and transient time series. So what we actually do, we take telescopes and conduct surveys where we pan across large areas of the night sky and we come back to them night from night. And so we take pictures or movies like this, not this nice, this is a simulation, where I can see galaxies other than our own. We can spot new stars in these galaxies. That's what I mean by this point here, that evolve over time. These aren't new stars, these are the explosive deaths of stars. And again, it's typically the light we see is dominated by the radioactive decay of recently synthesized elements in the bellies of those massive stars. To really understand the physics, the full kind of information signature available to us is captured in this rainbow GIF. You can see time here represents time. The y-axis represents flux, number of photons, and the x-axis represents wavelength or the color of that photon. And you can see kind of two things are happening. There's this bulk evolution that roughly matches a black body that's expanding with time. And on top of that, you see these fingerprints, which are signatures of elements that either existed on the outer envelope of the star when it exploded or was synthesized in the belly and is now being extracted into the universe. So if I really want to match my models to that data, I want to capture each of those photons at every wavelength and at every point in time. The issue is that that's really expensive to get what's called spectroscopic measurements of these things. Just one snapshot, even in time, can take hours even on an instrument. So it's really not possible to make these highly detailed time series. Instead, what we do is we take big bins and I ask questions like, what are the blue photons doing? So all of these versus all of the red photons. That's much easier. I can do that using an image like this that's sensitive to photons across a wide range of colors, and then sum those up to create, as a function of time, these curves. And I call these light curves. Although that's a kind of low fidelity, a low resolution version of that beautiful high resolution data set, I'm going to argue, honestly, not very much proof. So believe me, but feel free to ask me about it, that those lower resolution observations do actually capture the physics. In fact, we can think of some pretty simple observational feature spaces that we can create from these light curves that really do cluster the physics in ways we can almost immediately identify. Here's an example that's very common. How long is that bump in the night sky lasting, and how bright does it get? So a duration versus a luminosity. Something that's super long lasting, like decades, and is incredibly luminous, likely involves a supermassive black hole and accretion onto that massive object. In contrast, maybe if I'm incredibly short duration and low luminosity, there's an implication that if it's radioactive, I formed a very small amount of material. Perhaps that's something like the merger of two neutron stars and the following electromagnetic or light emission, which we call a kilonova. So the whole point of this is to say there's this incredible wide diversity of physical phenomena that we see in the night sky as these bumps. And our job is to try to connect that physics to the observations we see. This isn't just cartoon. This is a true quantitative statement. Here I'm showing a kind of an ugly plot, but a theoretical study we did of forward modeling just many discrete classes of high energy physics we can imagine. Is it shock driven? Is it driven by that radioactive decay? Is it driven by a highly magnetized neutron star? And we ask questions. We ask the question, given a reasonable range of models leading to these types of explosions, what is the contour of most likely feature space in this simple duration peak phase space? And again, I'm just emphasizing that in some cases, it's quite clear to point out the physics. You can see here, like long GRBs are relativistic events, super bright, super fast. These kilonovae are showing up again, the neutron stars, very dim, very fast. But there also exists a space here where there's substantial physical overlap. And so it's not just as easy as us extracting hand-engineered features, on this level at least, to be able to untangle that physics. So that's really what this talk is about. It's about how are we using our observations to untangle that zoo that we see, because these bumps in the night sky we see in the surveys are not labeled as the type of physics they represent. Okay, first some clarification here. Astronomy is a historic subject, which means it's confusing. And so we have this concept of classes, even in some of these subtopics of physics. And what I'm really going to focus on are supernovae, the deaths of stars. There's many different types of stars that can lead to a supernova. One of the most classic examples is I can either have a massive star, as I've been describing, that at some point tries its very best to fuse iron, realizes it's an endothermic process, and collapses on itself before bouncing off into a supernova. In that process, that chunky star has maintained its hydrogen envelope, so when it explodes, I see the signatures, the fingerprints of those hydrogen lines. Just due to historic reasons, those are called type 2. In contrast, if I'm a white dwarf progenitor, so held up by quantum pressure, I can eventually accrete too much mass from some sort of buddy that I'm paired up with, exceed a limitation in which my quantum energy pressure can no longer actually maintain stability. I once again collapse and I explode. And I don't have a hydrogen envelope because I've already evolved off the main sequence. And in this case, that lack of hydrogen, I would call this a type 1 for historic reasons. The main point here is that these classes are linked to the underlying physics, albeit through a strange set of observational cues. They're observational classes, but they're linking to the underlying physics. Unfortunately, the longer we watch for supernovae and did this process of classifying them into discrete buckets, we started to realize, okay, yeah, astrophysics gets in the way, and there's many types of ways we can die. In fact, it's not so easy to answer this question of do I or do I not see hydrogen in a spectrum? Sometimes we see something in the middle. And the more that we've observed, the more complicated this hierarchical taxonomy has gotten. But it's still our underlying way of doing classification. We take a spectrum, we ask a question about those lines that we see or don't see, and then we prescribe some physical model based on that. It is the case, though, that the shapes of these light curves also encode the underlying physics. And, I might skip the physical explanation here just to get to fun stats. So believe me, but you can ask me questions if you want to know more about why this might be. I'm also going to skip that for now. I want to say that we discover a lot of supernovae every year. 20,000 is probably generous, more like 10,000 annually, thanks to many wide field surveys. So those are those surveys that are taking lots of pictures of large areas of the sky every-ish night. But this has been a growing industry since the 80s. Here I'm just showing a plot of our discovery rate as a function of year of supernovae since on a logarithmic scale. And that's in blue. So in the 80s, we found about a dozen per year, and nowadays we find about 10,000. Remember that I said the taxonomy we've developed historically has relied on spectroscopic labeling. I need to get a spectrum to say what the class is. That gray line is showing you the number of events that have an associated spectrum. It's about 5 to 10% right now. And I'm being completely honest when I say that we throw away 95% of our data. If it doesn't have a spectroscopic label, we as a field don't really do anything with it right now. This is going to change in just a few years. At the end of 2025, a new observatory called the Vera C. Rubin Observatory, named after the lovely Vera Rubin, who discovered dark matter, is being built. So this is an 8-meter class telescope in Chile that's going to conduct a survey that's called the Legacy Survey of Space and Time, or LSST. I'm just going to warn you, I'm going to use Rubin and LSST interchangeably, probably. Same thing. The key point here is that that is going to be a really massive undertaking of a decade-long movie of the whole southern sky to this unprecedented depth, so dimness in the sky we can reach. That's really going to change the game for supernova science and time domain astrophysics more broadly. And so I'm going to show you that same plot once it gets to, I can see it, so I'm waiting for it to reset. There we go. So this is the same plot. And I'm showing you here that blue curve and what Vera Rubin is going to do to our discovery rate. So I'll say, keen eye will notice that I changed this to a linear scale to be dramatic, but it really is this like dramatic change of events. We have had exponential growth in our discovery rate for the last few decades. Vera Rubin is going to break this exponential growth by bringing us up 2 orders of magnitude larger in our annual discovery rate of supernovae. We're going to be discovering something like 1 million explosions every year. At the same time, there are some really wonderful planned surveys for spectroscopy to help us get spectra for these things. But even so, even if we're able to increase our number of spectra per year, so remember that's the traditional classifier, by a factor of 2 or 5, like that's a very small dent in this problem. And so if we just assume we don't really change at all, naively, we're keeping the same number of spectra per year, Now the fraction that receive a traditional classification is like 0.1%. So we can either throw away 99.99% of our data, or 99.9% of our data, or we can change our methodologies. And that's what we've been doing, or what we've been building towards. And I like to think of this exciting new era as having a set of needles and haystack problems. So the needle in the haystack is the most intuitive set of problems. We discover 1 million or so supernovae every year. Of those, let's say that thousands received a traditional class. Okay, sure. But as physicists and in this time domain field, we actually, based on the physics we see, we respond to those observations in real time. We often supplement these surveys with additional multi-wavelength observations. For example, if I see evidence of shock, so hot blue photons, then I might request X-ray observations to get a better idea of exactly what is being ionized and what is the ionizing agent. So when we start to make a cut that's just follow-up based, so multi-wavelength follow-up based, but also just like human hours based, how many of these events can we realistically study in real time? I'm conservatively just guessing about 100 events per year are going to have a wonderful little case study based on them. And if we just do basic math, that means that only about 1 in 10,000 supernovae are actually going to be studied in real time with any kind of additional follow-up. Last point to drive this home is just to say that this is really as if the field in the last year came together and said, of the 10,000 supernovae we discovered in 2023, what's the one we're going to study this year? Like, there's just a whole new level of thinking about what does it mean to be an important enough event to be worthy of our time for follow-up. A key point is that just because of these high rates, we are going to be able to really keep going down that hierarchy of the taxonomy. We're going to really be able to understand very rare states of massive stars and their unstable end stages, probably, of their nucleosynthesis. So I think what's so exciting is that we can, in theory, probe 1 in a million events if we can figure out how to be sensitive to them. I'm going to do a quick pause and see if there are questions. The rest is methodologies towards this overarching question. I don't see hands, so I'm going to speed on by. So really what we attempt to do, our downstream tasks, are, to me, sorted into these 3 topics of classification. What did I say? Classification, identification, and analysis. What I mean by that is a cute cartoon to help us out. Imagine that I see some explosions in the sky. I'm able to extract the mass of the thing that exploded, the star that exploded, and the kinetic energy of that explosion. I might notice that oh, these are probably backwards, but let's just call these blue ones type 1As or something, and these red ones type 2. I might ask questions like, hey, for this new object that's shown in gold, is this closer to a type 1A or type 2? That's what I mean by classification. Given our known set of physics, can we sort these objects into their classes and then conduct, ideally, hierarchical population studies with those classifications? For this gold star, that's a new object I've seen. It doesn't seem to lie in a high density region of either class. So am I able to identify anomalous physics that's actually novel, that's sitting in this regime because it's low energy, low mass, not because it's a weird glitch? And then the key last point is, in some sense, doing the physics, but in a statistical sense, I need to actually extract these meaningful latent features, these physical inferences from my observations. How do I do that quickly enough that I can scale up to the data rates we expect analysis to? So those are the 3 classes of problems we've been thinking about. And the way that we've tackled them, so now I'm just going to step through, has been largely turning to machine learning and more recently probabilistic machine learning methods, especially those that can extract what we would consider to be reliable, well-calibrated Bayesian posteriors of inferences.
Ashley, there's
Of
a
course.
question on chat.
Oh, yes.
So yeah, I can read it.
Okay.
What's the main limiting factor for getting spectroscopy data for events in addition to just luminosity?
So I want to make sure I interpret the question right. So it's time, as in it is, it's expensive for me to capture spectrum versus photometry measurement, and think of that just because of the binning. I have very precise bins over wavelength versus photometry is a very large bin over wavelength, so I get signal to noise very quickly. I think that's not quite what you're asking. I think you're asking though, oh, can you not get spectroscopy because they're all too dim? And that's true. Some are so dim that it's prohibitive to get spectroscopy, but even for the bright events, there are too many to really get a large fraction of those. So I hope that answers the question.
I think so.
Okay,
Thanks.
great. Let me put up my, okay. Good. Sorry. Okay, so the way we're going to do this, we're going to extract features from our transient light curves in order to do this classification. In other words, like I have, oh, I didn't show a nice picture of this. Huh, that's annoying. So I have irregularly sampled multivariate light curves. I'm sure I didn't show you this. That would have been very helpful for you. I think I have it just out of order. Here's a nice example. Oopsie. So these points actually represent our observations. This is time, this is flux. Ignore for right now these fits in the background. This is just to say, like, it is multivariate. It is, these aren't actually too sparse. It's going to be a lot sparser in LSST. And so our first task is to just turn these light curves, these pieces of data, into fixed length vectors so that we can actually play these kind of clustering games. Ideally, low dimensional so that we can play them efficiently. One of the issues is because there's a diversity of physics, there isn't like one physical model to rule them all. I don't just have one supernova model to play with. So what we've done around this is to just create an empirical model that looks something like this, that roughly captures what we expect to see. In general, these things go boom, they get bright, last for a bit, fall off. Okay. We can then fit these models to our data to create latent spaces. We don't know, of course, the exact combination of how these parameters should relate to one another to create a probability of being of class type 1 or type 2. We also don't know if this would be a natural, just linear combination of these parameters or not. And so for those reasons, particularly that we suspect a nonlinear combination, it will probably be helpful. We use, not all the time, but for the sake of this talk, I'll say that we use neural networks to give us this nonlinear mapping from our observational feature space to our classification probability or pseudo probability. Do I have to explain neural nets? I think that's actually a question for this audience. I'm happy to in like my 2-minute description. And does the audience know what a neural net is?
I think most people do, and they welcome to ask questions if it's needed.
Okay.
Thanks a lot.
Okay. Feel free to ask if you don't know. That's fine. Just ask. But I might assume that you do. Right. So we're just using this because we want an efficient method, and I'm kind of lying. We also very often use tree-based methods to do these classifications as well. Okay, so at this point, this actually has become a pretty common task for us, and we've gotten, I think, pretty good at it. Here I'm showing a confusion matrix, so I'm just comparing how often am I getting the predicted label correct, so matching the true label. That's what these matrices show. And what we're typically looking for is that our diagonal line is a dark color, that we have high agreement between the truth and the predictions. I think the key thing I want to say here is you might look at this and say, well, I'm not actually convinced, Ashley, that you're doing a great job because you're not at perfect scores across the board. I would say it's an open question at this point if we're doing optimal feature extraction, or if we're really at this point like limited by that low resolution of the data itself. And the fact that the physics can look quite similar for these events, even if it's different classes, especially because all of this is thermal physics. It's all black bodies evolving with time for the most part. And so the diversity you see here is actually a reflection of a few things. The universe is not creating all these explosions equally. Type 1A supernovae are about half of our entire sample because they tend to be bright, so we can kind of see them further away. But more importantly, these things famously all look the same. They're standardizable candles used for cosmology. So it turns out it's really easy to classify them because you don't have a lot of diversity in your observed population. Contrast that with his buddy, who's one of the worst of the performances, type 2N. These are really massive stars that have some sort of unstable mass loss near the end of their life, and they like pollute their neighborhood with star stuff. And then when they blow up, they run into that star stuff and they create shocks that we see in the light curve. Huge diversity in these things. And they make up a very small fraction of the supernova population. And so we really just don't quite perform as well because they're easily confused for other events. Okay. Oopsie. This is to emphasize, I'm going to quick go through this. I just want to emphasize that, again, like at this point, classification is a very common task. It's not a solved task, but using the light curves themselves to guess at the spectroscopic labels has been done for a number of surveys. We did it originally in the Pan-STARRS medium deep survey of a few thousand supernovae. We're doing it right now with the Zwicky transient facility, again with now closer to 10,000 supernovae. And we've done it recently with the young supernova experiment, which I've largely skipped over, but another large survey that my team is a part of that had a release of, again, thousands of supernovae, photometrically classified. This is becoming standard practice. This is great for archival studies. So if I wanted to go back and look at the haystack and ask questions about the underlying population, and that's the next direction forward in that research. But there's this other half of following up events in real time. And in particular, there's a lot of open questions that can be probed at the very youngest stages of these explosions. At the very early times, when my ejecta is still close to the inner part of the star, I can probe, if I'm really lucky, the outer layers of the star right before it exploded. You can only do this, though, if you can act really fast. And so there's this fun question of, can I even classify supernovae with no photons? Like, can I just figure it out before anything happens? And it might sound a little ridiculous. My computer's thinking. There he goes. But the path we have forward is that supernovae that we observe are all happening in galaxies other than our own. Our Milky Way rate of supernova about once per century, and so we're not like sitting around waiting for those. We see many galaxies far away at a high volume, and we're watching them go off in those galaxies. And galaxies are just collections of gas and stars, and the supernova is a biased random sample, but like a sample of the stellar collection in that galaxy. In other words, I actually know about the neighborhood I was born in and the one that I died in. And so there are some correlations between the properties of that galaxy and the type of explosion that it creates. Apologies, a little bit of a confusing plot here, but this is just attempting to show you that even in like some linear breakdown methods of images of galaxies, you can slightly detangle different classes. There are some very clear physical reasons for this that I will skip. I apologize. It turns out we can do actually pretty well. We can get, so this is what, a completeness plot, a confusion matrix again. Here I'm just showing that we can actually do a pretty good job of at least asking a question. Did you die from a massive star or something that is much older, like a white dwarf? This 1/8 versus a type 2-ish question. We think we can do better. And one of the ways that has been quite fun that we're exploring this is we've been training neural nets to think really hard about what galaxy images are telling us. The way we do this is that we train a neural net to do the following: to predict the physical parameter, given an image of a galaxy, try to predict its physical parameters, so its redshift, its distance away from us, how massive it is, how much star formation is going on. Compress, and in addition to that, try to also encapsulate in a low-dimensional vector things that we can't quantify as well. How spirally, this isn't a very good spiral, but spirally is the galaxy? Elongated, compact. That's called the morphology. And there aren't great quantitative metrics of that, but it could be captured in a specialized neural net. When we do this, we train a neural net to obtain these properties. We find that we are able to do a good job in the images alone, predicting some of their fundamental parameters that I mentioned, redshift, mass, etc. But then what's really fun is that we've designed in such a way that we can also get generative samples from this learned representation space. And more importantly, we get density estimates, so we can ask questions about how weird a galaxy might be. So I'm showing you here just what happens when I fix every dimension in my learned latent spaces, except for one, which I will vary linearly. So in this case, I'm varying the angle, the position angle of that galaxy, what angles it rotated at. And you can see that, yeah, changing this value and keeping all else fixed allows us to see how we can rotate these galaxies. When we change something that's trained to represent redshift, we see that as we move farther away, that's higher redshift, these objects become dimmer and redder, which is what we expect. With higher star formation, we find that these things become blobbier. I'm not sure if we expect, but they become bluer. And then we even have these now, like I said, hard to quantify with known metrics, but something that can be captured in the neural network. These truly just latent features that we hope now represent morphology. And indeed, we do kind of see that as we tune this, we get drastically different morphologies. So one thing that's been exciting about this is looking for real weirdos in this learned latent space. And what we're excited now to apply it to is connecting it to supernova science and trying to find supernovae or stars exploding in these weirdo galaxies. Because as it turns out, often if you die in a weird neighborhood, you probably are a little bit of a weirdo yourself. And so there's often really exciting high-energy physics there. Okay, so that's ending the classification set of fun methods we've been working towards. Again, we'll very briefly see if there are any open questions. I'll say with that galaxy bit I just explained, for people in the know, we used an autoencoder. For people not in the know, we're about to see what an autoencoder is. Okay. So we still have this question of identification, right? Where like, okay, I've made this latent space, I've clustered things, I've classified things, but what happens if I'm in a weird low density region? How do I find the 1 in a million rare physics? And in particular, we want to do this in real time. And one of the issues that we have with the classification scheme I've presented, the one where we fit the light curve to get parametric features, is that obviously we have a lot of uncertainty for features that depend on the later portion of the light curve. So these aren't great for helping us find really interesting events in real time. Instead, what we're going to do is again turn to deep learning, and we're going to create a specialized architecture using an unsupervised approach. Meaning, okay, I'm not going to tell this neural net the classification types of all of my supernovae. I'm just going to show it many examples, and I'm going to ask the question, how weird is this next example that I've shown you? So that we use this variation of recurrent autoencoder, and we will go through the adjectives together of why we made these decisions and what they mean. So an autoencoder is, I think this audience knows, just a neural net in which I've set up the architecture so that there is a compression and expansion allowed of my data. I have a large set of input features. I reduce those down to a small latent vector, but then to reproduce the data, I allowed it to expand it again. The objective function, the cost or the loss function of this, is to take the initial light curve I give it, that's some matrix, and I just say, give me back the same thing. I want you to show me the same light curve. But by having this compression step, I am reducing the dimensionality at some point in a nonlinear way to this nice low-dimensional fixed vector that represents my latent space where I can ask density estimation questions. Okay. I'll note that we use a variational autoencoder, where here we just have to think of this as, instead of encoding each light curve to a singular vector, I think of that more as like a vector, and then it's associated as a density function, where I'm describing that from that density function as the first two moments. So it's like a Gaussian, it is a Gaussian, so it has a mean and then a standard deviation. We're gonna use that for another reason too, but that's good enough for now. The last thing we do is this recurrent neuron setup. And this makes sense. As we get, I'll take a step back, sorry. Recurrent neurons simply take in, they have knowledge of not just the current input you're showing, but also the previous versions of that input. So how that's dynamically changing in time. We're going to use this because we have actively changing time series, and we want to update our embeddings, our latent features in real time, presumably getting better at representing the data as time evolves. So that's our variational autoencoder setup. I'll show it in action. Here, this is again real data in the points, and this is time in days. This is a measure of luminosity that comically, historically has like a negative log function. So just, these really are brighter, these are dimmer. Okay, so these are real points. In this data, this is the only high signal to noise point, this Z-band point. But these lines are showing you the output of our variational autoencoder, what we think the data looked like interpolated and extrapolated. It doesn't do a very good job, admittedly, with a single point. That's fine. Once we get a little bit more data, our VAE actually does, so sorry. Our VAE does a better job at correctly representing at least the correct peak luminosity that we expect for this type of supernova. And I know this to be true because we had a spectrum of the supernova. I knew its class. And so this is the one where they all look the same. And so I knew it would be roughly minus 19. With even more data, it does a better job at the encoding. Not perfect, but it even picks up on these secondary features. So type 1As notably have this secondary bump or plateau in the redder bands. So Z is quite red here. So that's great. And our final estimate, again, while not perfect, is a fairly good representation of the data. So what our variational autoencoder allows us to do is to build this new latent space that's not dependent on physics. It is not rooted in a singular physical model. It has been exposed to the full diversity of physics that we see. We can then just, there's a question that says, do the predictions come with some sort of uncertainty estimate? Yes, with a caveat. It would be cool to see the prediction intervals getting smaller and smaller. Yes, I have that, but I'm going to make a big caveat when I get to it. So I'll get to that in 1 second. So now that we have these features, we can just make a scatter plot basically. And so imagine, I think this was 10-dimensional-ish when we did this study. But just imagine here for visualization, I make a scatter plot of a 2-dimensional subspace of it. And importantly, all of my points are here shown as dots. And we can easily look for anomalies using just a number of density estimation functions or anomaly detection algorithms. So in this case, we use an isolation forest, where I basically just make some cuts in this space and ask, hey, can I isolate you really easily using just a few cuts of my space? I really want to point out, though, that part of the reason why this works so well, and really why we use the variational autoencoder, is because variational autoencoder has a regularization term that essentially acts as a prior on the latent features. It really wants it to look like a multivariate normal distribution, and you kind of see that being true. Most of them want to sit at 0, 0 with a spread of 1. In the case of anomalies, those really cannot be pushed towards that center, and that's why they stick out as these low density regions. Okay, we did all of this on a really cool open source giant simulation of what we think LSST is going to see. That's called plastic. And so importantly, everything was tagged with the right answer. So we could do this in an unsupervised way, but then we could go back and actually ask the question, the things that you called anomalous, were they actually scientifically interesting? And the answer was largely yes. I'm not showing plots about that. I'm just showing you in one example. This is a rare type of supernova. This is its light curve. This is showing a different slice of that feature space where each point represents a random supernova in the sample. And this is not a great plot, but what this is supposed to show is what happens over time in this latent space as we get more data available, and that's being shown as opacity. So low opacity is at early time. I only have a few points. I'm basically in the cluster, and then I kind of walk away from it as I get more data. And what that means is as I walk away, it's getting more and more obvious that I must be an anomalous event. And what's exciting is that I reach some threshold of our anomaly score. I can't remember if it's like 1% or 0.1%, really early on in the evolution. That's what this plot is showing, the scaled features as a function of phase relative to mass. Okay, cool. So that's all to say, it seems like these sort of strategies could work for identifying real physics in interesting physics in real time in the era of LSST. So we're now working towards having similar models that can work in real time before LSST is up and running. So on the Zwicky Transient Facility and on the Young Supernova Experiment.
Actually, you have about 10 minutes.
Yes, perfect. Okay. I want to go back to this question. Do you get error estimates? Yes, but I don't think I did this very well. I do, but because I just have this very vanilla variational autoencoder, I heavily encourage that those uncertainties end up being close to 1, and you see this exactly happen. They're not, they shouldn't deeply believe in these uncertainties. I think the right thing you could have done is attach a flow or something to this at the end to get out something that's a bit more meaningful. So the answer is, yeah, I have uncertainties. I wouldn't really trust them heavily. Yeah. Okay. So the last thing, which I'll go through, is to say, okay, awesome. We have classified known physics. We've maybe identified interesting novel physics, but now we have to do physics. So if I know what class you are, I can, in theory, now choose my physical model that I would like to use to infer the underlying explosion properties. But now I have to actually fit the data. Fine. We're okay at doing this in the field. Traditional fitting for supernova science, so fitting these time series to fitting a model to these time series takes tens of minutes if you're not doing a great job to more hours per one supernova. The traditional methods are a very classic Bayesian inference techniques. People typically use or nested sampling. I want to say that this is an oversimplification, but MC takes a long because we have to make many model calls. In order to sample properly from that posterior, I need to do this back and forth dance in which I choose a set of model parameters to try. I compute the forward model, the physical model, compare it to my data, go back and try a new set of parameters based on what happened. So if I want to do traditional fitting on the full sample of LSST, so after 10 years, that's 10 million supernovae, something like 10 million CPU hours. This might not sound like a big problem to some people in the room, but I want to actually emphasize it's worse than it sounds, because I don't actually, for the vast majority, in fact, technically all of these supernovae that don't have a spectrum, all of my classifications are probabilistic. So the right thing to do, if I want to do true population modeling, is to fit every single type of physical model I have at hand to every single supernova, and then correctly weight the probability that class was correct. So this very quickly scales this up to more like 100 million CPU hours, which maybe it's manageable, but let's make it even easier. So the way we're going to speed up this technique, the first thing that you might just guess to do is, okay, do some form of variational inference. Make some strong assumption about the shape of those final posteriors, like it's a Gaussian, and then just fit that way. That's fine. Many of you might know this. That's a fine assumption. It turns out it's not great for fitting in most of our cases. Our posteriors are not quite close enough to a Gaussian to be well approximated by this. And this is just showing a toy example of, it might take actually a large mixture of Gaussians to properly represent the posteriors that I'm expecting. But you could imagine that I could do variational inference if I had instead some really clever idea of how to transform my proposed distribution of the Gaussian using just a simple set of transformations into an arbitrarily complex posterior. So I have this cute GIF that shows an example of what I mean. All of this I should cite, I've stolen online. So here I start with this kind of multivariate Gaussian, and each point has its own set of rules to move forward to transform itself into this two moons intersecting distribution. This concept is called a flow. And what we've been working to do is to train specialized neural networks that include these flows to basically look at many examples of pairs of simulations, where a pair consists of the underlying physical property we're trying to infer. Here, pretend this is the mass. These don't make any sense, but this is, I guess, is the ejecta mass of the explosion. And this is the observed light curve that we should see with it. I show those pairs to this type of neural network. And instead of explicitly telling it what my likelihood function is for doing this inference task, I can instead say, hey, learn like the joint probability between the features I show you, the light curve, and the properties I would like to infer, this mass. Then, after I've trained up that neural net, which is computationally a little expensive, not that expensive for us, I can condition, in test time, I can condition that neural net on a new observation. I can show it this light curve. And in a pass of the neural net, I can get a sample out of the full posterior that now has built in, thanks to this flow, a flexibility that allows it to be arbitrarily complex. Sorry, I clicked on the wrong thing. Did this move forward? There you go. So we did this. I did this on a, again, simulated set of supernovae with a generous LSST simulation, as in, this is a very beautiful looking light curve, but I was generous with it. We trained a simple SBI, a simulation-based inference model, so one of these flow-based models, to take this data and to give us out posteriors for our basic physics we expect. And we found, I'm not showing you this, but we found that it was well calibrated. Our posteriors, they are well within what do I want to say? Not the precision. The precision is true of our traditional methods, but not only that, we have meaningful posteriors coming out of this. And what's exciting is that it takes really only like easily less than a second per supernova. In fact, something like 10 milliseconds if we could speed it up. So that's only like a day on my laptop to do the entire set of supernovae available in LSST. What's exciting about this is you can really start thinking about one, doing those full 10 million events, but also doing like really interesting ABC type of calculations to understand what biases are playing, what observational biases are playing into these surveys that feed into the eventual population inferences I want to make. I only have 5 minutes left, so I'm going to mainly make this an advertisement. In a different context, we thought about, again, using these simulation-based inference approaches to work with real data, and realized that real data is super messy. So with this really wonderful postdoc, Binji Wang, and wonderful collaborators, Josh Spiegel and Joel Lija, we thought about how can we use the similar really fast inference technique on galaxy fitting. So thinking about how does the light of galaxies translate into the properties of those stars and gas that makes it up. I'm going to ignore this for now. Basically, we played a little bit of games with SBI to help it work with real data. I'm happy to answer questions. The main thing I actually want to just note is one thing that really surprised us is that in this task, we found that our new methodology, I'll say that, compared to traditional Bayesian techniques, was like surprisingly better calibrated. Here I'm showing you a measurement of a galaxy's distance that's very precise, the spectroscopic measurement, versus the prediction from the light that we see from that galaxy. In black, I'm showing you the traditional Bayesian inference technique, nested sampling. And in red, I'm showing you our inferences from this new technique, which we call SBI++. We get larger uncertainties here, but the point I'm really telling you is the fact that we at least get these large uncertainties when they should be correctly applied. There's a well-known degeneracy between these two solutions. I'm either at this kind of low redshift or this higher redshift regime. And in our new method, we at least are able to capture the uncertainty between those two modes of the solution, whereas nested sampling, surprisingly, is more often than not getting stuck in one of these modes. Okay, so I'm going to end there and just leave up my slides and say thank you so much for listening.
Thanks so much, Ashley.